Hi, welcome to the random walk. What is it and why do we care? Let's take an object located at the position x equals 0. It will take a series of n steps. Each step will either be to the right, which we will call the positive x direction, or toward the left, the negative x direction. Each step will have a size of 1 unit. So, after the first step, the object can be at either x equals -1 or x equals +1. The direction of each step is random. It goes to the left or right, each with 50% probability. Additionally, the steps are independent. The direction the object goes on one step does not affect the probability of it going left or right on any other step. What we want to do here is find the probability of the object being at a particular location after n steps. So, at n equals 0, the object is at x equals 0, as it hasn't gone anywhere yet. At n equals 1, the object can be at x equals -1 or x equals +1. After 2 steps, the object can be at x equals -2, 0, or +2. After n equals 3 steps, the position can be -3, -1, +1, or +3, and so on. The object can be at locations ranging from -n to +n in steps of 2. But these ending locations are not all equally probable. We want to find the probability of the object being at each possible ending location. Okay, this is a simple example of a random walk. Why are we interested in this? Well, there are many good reasons to be interested in random walks, but here we're specifically interested in how Gaussian distributed errors arise in measurements, and it turns out that random walks are really useful for understanding that. Now, previously we looked at the relation between the measured value for some quantity, which we called q measured, and the true value of that quantity, which we called q true. Because of measurement error, these will not be the same. Many sources of error will cause q measured to differ from q true. These sources are represented here by these yellow arrows. We take these sources of error to be highly dependent upon the setup of the experiment, and they vary randomly from trial to trial. So if we do the experiment, the different sources of error might look like this. If we do it again, they might look like this. And if we do it again, it might look like this. We take the sources of error to be independent of each other, so the size and direction of one error source in a trial doesn't affect the sizes or directions of the other error sources in that trial, or in other trials. We said in a previous video that we don't want a scenario where the error is dominated by just one source, or by 2 or 3 sources. Gaussian errors arise when there are a bunch of error sources that can largely cancel each other out. This happens if the most important error sources, which means the sources with the largest typical sizes, are of a similar typical size to each other, and there are a bunch of them. Let's say there are n sources of error that are bigger than the rest and of similar typical size to each other. Any other sources of error are small enough that we don't have to worry about them. If n is small, say 1 or 2 or 3, we can't really expect the errors to be Gaussian. But if n is large, that's when Gaussian behavior shows up. Here, we're going to make a crude model of this. We will look at the n most important, i.e. typically largest sources of error, and we will ignore smaller sources that won't affect the overall error very much. And since we're interested in the case where the n most important sources are all of similar typical size, we'll model the n most important sources of error as all being the same constant size. So we'll go from this realistic situation, where the difference between Q measured and Q true is a sum of many errors of different sizes, to this simplified crude model, where there are n error sources and they are all of the same constant size. While the error sources all have the same size, their directions will be random. Some will push Q measured up and some will push Q measured down relative to Q true. We want to look at the sum of these n sources of error. Let's look at how this corresponds to a random walk. A given source of error can push Q measured up or down. At a given step in a random walk, the object can go to the right or left. So we're going to represent an error source that pushes Q measured down as a step to the left, and an error source that pushes Q measured up as a step to the right. We have n sources of error, so we have n steps in our random walk. So basically, in this crude model, we are approximating Q measured as Q true plus the error source size times the result of the n-step random walk. When we do one iteration of an n-step random walk, by which we mean letting the object take n steps and we see where it ends up, that represents one experimental trial, or in other words, one measurement. So in our first measurement, the error sources might have looked like this, while in our second measurement, they might look like this, and in our third, they might look like this. So, for example, if we had n equals 3 dominant error sources, and we have an experimental trial where the first error source pushed Q measured down, and the second and third pushed it up, we would represent that by a random walk where the object steps to the left and then steps to the right twice. And if we have another experimental trial where the first and third error sources push Q measured down and the second pushes it up, we represent that as a random walk where the object steps to the left, then to the right, then to the left again. In short, to understand the realistic situation where Q measured gets contributions from a bunch of error sources of different sizes and directions, we're approximating it as getting contributions from n error sources that are all of the same size, but randomly pushing Q measured higher or lower. And then, to model that, we're going to simulate an n-step random walk. When n is small, say 1 or 2 or 3, we won't see anything too enlightening. But when n gets large, we'll see Gaussian behavior emerge. And this will be our first step to understanding how Gaussian errors arise in real-world measurements. We will be looking at random walks with 1, 2, 3, 5, and 15 steps. We'll look at the average expected results for each of these cases. But we'll also do simulations to demonstrate the statistical nature of the random walk and of measurement errors.